Welcome back. Today we're going to talk about partial derivatives, which give us a way to take derivatives of functions that have multiple input variables. So how to take the derivative of a function that looks like f of x, y, z when we have multiple inputs there. The idea behind working with partial derivatives is to take the derivative with respect to one variable and treat all the other ones as though they are constants. And today we're going to work through a few different examples of how this would work out. So let's go ahead and get started with that. So let's go ahead and get started with an example to see what this looks like. We're going to find f sub x, f sub y, f sub z for f of x, y, z equal to x, y, z plus x squared y plus y squared z plus z squared. And I do want to take just a quick second to talk about some notation. The little subscript here on each of these functions is going to tell you which variable you're taking the derivative with respect to. So let's go ahead and start with finding f sub x of x, y, z. And we have a little bit more notation that we use to talk about partial derivatives. It's very similar to notation that we use to talk about derivatives that you're already pretty comfortable with. And that is to take this kind of script d over script dx. This symbol right here kind of looks like the ASIC sign from tennis shoes or something. It's called a partial because they're used in partial derivatives. And it's the same idea as taking d dx, where what comes afterwards in parentheses or whatever is up here in the numerator tells you what you're taking the derivative with, what you're taking the derivative of, and then this tells you what variable you're going to use. So this says we're taking the derivative of x, y, z plus x squared y plus y squared z plus z squared with respect to x. So same idea as the standard notation that we were working with before. So now all we got to go through is take the derivative of each one of these pieces with respect to x, and we're going to treat the y and the z as though they're just numbers. So when we take the derivative of this piece right here with respect to x, the x just becomes a 1, and then it's still times y, z, because we're just treating those as though they were numbers like 4 and 5, and if they were just 4 and 5, they would stick around and just be multiplied by the 1 from x. Same idea here, we're going to have 2x, and then the y just sticks around because we're treating it as though it's a number. And then these last two terms, though, because there is no x attached to them, there's no x involved in them at all, again, treating them as though they're just numbers, they become plus 0, because if this were, say, a 4 squared times 5, we would be getting 0 out of that derivative, okay? And then same idea here with the z squared. So then our final answer here is just y, z plus 2x, y. And that's for the partial derivative with respect to x. We can do the same idea with y, and it uses very similar notation. So I'll have partial with respect to y of x, y, z plus x squared y plus y squared z plus z squared. Okay, so again, treating the x and the z this time as though they were numbered and taking just numbers and taking the derivative with respect to y, we're going to get that the y becomes just a 1 when we take the derivative of that, and then we're just left with the x and the z. And then here, when we take the derivative with respect to y, only the x squared is left behind, because that's what would happen if x squared were just a number. And then here, we get 2y times z. And then this z squared is just a 0 because it's not multiplied by y or anything. So since it's just a constant, it goes away when we take the derivative. So our final answer is just xz plus x squared plus 2yz. And then finally, we can take the partial with respect to z. And this is equal to partial with respect to z of xyz plus x squared y plus y squared z plus z squared. This, we're just left with the xy because the derivative of z is 1. This becomes 0 because there's no z attached to it. This becomes just y squared. And then this right here becomes 2z. So it's pretty straightforward. And I mean, we get to use a lot of the same derivative rules that we already know from working with just like the f of x is equal to y type functions. So pretty straightforward. It's just, again, you take the derivative with respect to whichever variable is listed here, and then you treat the other ones as other numbers. So like I said, the same derivative rules apply. And that goes beyond just the whole x squared equals 2x thing. This also includes our product quotient and chain rules. So let's work an example showing how all of those work out as well. We're going to find both partial derivatives for f of xy is equal to x squared cosine of xy divided by y cubed. Okay. So first we're going to find derivative of f with respect to x of xy. And this is just partial with respect to x, x squared cosine of xy divided by y cubed. And I'm going to go ahead and we can factor this denominator out to the front because we're treating it as though it's just a constant, and it'll kind of simplify things down a little bit if I bring it out to the front. Okay, so again, this comes out to the front because it's just a number. And then what's left behind is the partial with respect to x of x squared cosine of xy. Now, in this situation right here, the variable that I'm taking the derivative with respect to, x, has two pieces to it, right? There's the x squared, and then it's being multiplied by cosine of xy. So here, we're just going to have to apply our standard product rule, which would look something kind of like this, partial with respect to x of x squared times cosine of xy being left alone, and then plus x squared times the partial with respect to x of cosine of xy. Okay, so we have 1 over y cubed, and then partial with respect to x here is just 2x, and then times cosine of xy. And then we're adding to this x squared times the derivative of this right here. Since we have x times y inside of cosine, we're going to have to apply our chain rule. And I'm going to get y times negative sine of xy, okay? Because this y here is the derivative of the inside of the cosine. So that's just 1 over y cubed times 2x cosine of xy, and then minus x squared y sine of xy. Okay, so this is our partial with respect to x, and again, we had to apply the product rule because there were two functions of x that were being multiplied together. Now we can take the partial with respect to y. So there should not be a comma there. Y cubed. Okay, so now this time we can't factor the y cubed out to the front because we're taking the derivative with respect to y. So we're no longer treating it like it's just a number. The x squared could come out to the front though, if we wanted to do that. But I think in this particular instance, I'm just going to go ahead and leave it and let it follow around for the rest of the problem here. So since we have a function of y on top and a function of y on the bottom, I'm going to have to use the quotient rule. Okay, and I think I'm actually going to need a little bit more space than what I've allowed for here. So let's just kind of. All right, so our quotient rule says low-d high minus high-d low all over low. If you've heard that before. So we have y cubed times the derivative, or the partial derivative in particular, still of x squared cosine of xy from the top, and then minus x squared cosine of xy times the partial with respect to y of y cubed. And then we're dividing all of this by y cubed squared. Okay, so now all we got to do is take these two derivatives right here and then kind of simplify some things down. So we have y cubed, and then since we just have an x squared here, there's nothing in terms of y. All we have to do is apply the chain rule to this, no product rule needed. So I have x squared, and then this will be times minus the derivative of the inside here with respect to y is going to leave only the x, and then sine of xy. So that's the derivative of this piece here, and then minus x squared cosine of xy, and then derivative of y cubed is just 3y squared. And all of this is over y to the 6th. So I've got y cubed x squared, and actually this is negative, and then these two x's are combined and we get an x cubed as well, sine of xy minus 3x squared y squared cosine of xy all divided by y to the 6th. And if we want, we can simplify this down a little bit by canceling a y squared from each of these. So we'll get negative y x cubed sine of xy minus 3x squared cosine of xy divided by y to the 4th. Okay, so again, main idea here, we had to apply our quotient rule in terms of y because we had a function of y on top and a function of y on the bottom. But since we were taking the derivative with respect to y and not with respect to x, we were not worried about the product rule in this case. All right, let's look at taking second order partial derivatives. So when we take a second derivative, generally, we just simply take the derivative again. Well, this time we have two options for taking derivatives, which means that in total, when we can take derivatives twice, we're going to wind up with 4 partial derivatives. So f of xy has 4 second order partial derivatives. And so one of them is, so we have fxx, so this is taking the derivative with respect to x twice. We can also write this as partial with respect to x of f of x, or fx, and then also, like, you may see it written kind of like this, just to kind of give you an overview of what some of the notation looks like with this. So this actually is really, really similar to what you're probably used to seeing with the second derivative when we're working with just f of x is equal to y, where you have the little squared term on the x and the little squared term on the d there as well. So this is one partial, second order partial derivative. Another one is fxy, which is when we take the partial with respect to x and then take it with respect to y afterwards. So this is what's kind of a little bit different than what maybe you're used to working with is that we're able to mix and match what we're taking our partial derivatives with respect to. So that's the partial with respect to y, f of x, and then it gets denoted just like this, where the dy and the dx are separate there in the denominator. All right, so now we have a couple where we can start with y. So f of y, or the derivative of f with respect to y, and then take that with respect to y. So like so. So partial with respect to y of fy similar notation to what we had up here. And then we can take the partial with respect to y and then with x. Just like so. Okay, so something that I do want to point out is notice that the first one listed is the first derivative taken. It's kind of easy to get the notation turned around, so I just want to highlight that for you, that we always read from, I mean, like, it's going to sound kind of intuitive, I guess, from left to right, but just make sure that this is the first derivative that you're taking. Okay. All right, let's work some examples. Okay, here we go again. In this example, we're going to find all second order partial derivatives for f of x, y is equal to x squared y cubed plus x plus cosine of y squared. Okay, so in order to be able to do this, the same idea applies here as when we were working with derivatives for f of x is equal to y, in that sense that we have to find our first order partial derivatives first. There's going to be two of them. So we'll start with fx at xy. So this is the derivative of f with respect to only x, and that's going to give us 2x, so that's the derivative of the x squared. The y cubed gets treated as a constant. We have plus 1 here from the x, and then this cosine y squared is actually going to be 0, because plugging y squared, it's just a number into cosine, so this is all still just a number relative to x. So that part goes away. Okay, so now we have the partial with respect to y instead. And this piece here, we're going to get 3x squared y squared, okay? And then this x is going to go away. And then right here, we're going to have to apply our chain rule. We're going to get minus 2y sine of y squared. Okay. That's not super legible. Minus 2y sine of y squared. There. Okay. So now all we have to do is take the other two derivatives of each of these. So we'll start with fxx, xy. So this is the partial with respect to x applied to this right here, to xy cubed plus 1. And that is just equal to 2y cubed, and then the 1 goes away. We can find our first mixed partial, which is starting with this fxyy, but now we're going to take the partial with respect to y next instead. And this time we're going to get 6. The 3 comes down from the y, multiplies by the 2, xy squared, and then the 1 is going to drop off. Next, we have fyy. So that's the partial with respect to y of this guy here. So 3x squared y squared minus 2y sine of y squared. And this right here, this one's pretty straightforward. We're going to get 6x squared y. And then this piece right here is going to require the product rule and the chain rule, because we have this 2y multiplied by the sine of y squared. So I'm going to have minus, it'll be 2 sine of y squared, and then plus 2y times cosine of y squared. So I guess we can distribute that negative and simplify some things down a little bit. We'll get 6x squared y minus 2 sine of y squared, and then minus, distributing that negative through, 4y squared cosine of y squared. Okay. And then finally, we have our other mixed partial fyx of xy. So that's the partial with respect to x of fy. So 3x squared y squared minus 2y sine of y squared. Okay, this piece right here just gives us 6xy squared. And then this piece right here, because it's everything in terms of y, it's just a number. So when we take the derivative with respect to x, it's going to go away. So yeah, that's pretty much all of the mixed partials right there. Main idea here is you just, you start with your 2 first order partial derivatives, and then you kind of mix and match all of the possible partial derivatives, and you'll get all the possible combinations there, which in this case is just 4. Something that I do want to point out, though, that's really, really important here. Notice how fxy is the same answer that we got for fyx. This will always be the case as long as all your functions are continuous. And this actually has a name. It is called Clairaut's theorem. So really important there. Again, just the main idea is that it doesn't matter which order you take your partial derivatives in. You can do it with respect to y first, or with respect to y first, and then with respect to x first. It doesn't matter. You'll get the same answer each time. So as long as all of your functions were continuous. So, but yeah, that's pretty much it for taking partial derivatives. Again, it's pretty straightforward. A lot of the same rules apply that we learned in Calculus 1. Going forward, we're going to start learning how to apply these in different contexts, like working with planes and linear approximation and stuff like that. So I'll see you then.